Okay, so we are integrating N of E, and N of E is basically the product of density of states and the probability density function f of E, which is the Fermi-Dirac distribution function. And density of states in the conduction band, it varies like square root of E minus EC. Okay, so now if you look at the Fermi-Dirac function again, our EF, if we take here EF, if energy is so EC minus EV is of the order of so let us look at some estimate values of EC minus EV. For example, for silicon crystal, EC minus EV, which is our energy band gap, is of the order of 1.1 electron volt. For room temperature, for room temperature, this KBT is of the order of 0.026 electron volt. So what you can see is that if you compare EG and KBT, we can see that EG is much greater than KBT. Now if I assume that our EF is somewhere, so this is our EC, and if I denote similarly EV, and then I am saying that EF is somewhere in between EC and EV, so then I can say that EF is roughly EC plus EV by 2. Okay, so if I take EV as 0, then it is EC by 2. So if I take the origin for energy as EV, then it is EF is basically EC by 2. So the point is that EC by 2, if I compare, so therefore EF, which is in middle of EC plus EV by 2, so which is of the order of 1.1 divided by 2. So let us take EV equal to 0. So that will give you EF equal to 1.1 divided by 2, which is EG by 2. So that is equal to how much it is? 0.55 electron volt, and which is much greater than 0.026 electron volt. Okay, so I just want you to, which is basically our KBT at T equal to room temperature 300 degree Kelvin. So at room temperature, our KBT value is 0.026 electron volt and EF is EF is basically 0.55 electron volt. Now why I do this is because our f of E function can be simplified under this assumption. So therefore f of E, which is equal to 1 by 1 plus e raised to E minus EF by KBT. So if you take E as EC, that is the bottom of the conduction band. Okay, so if I take this as EC, so EC minus EF, which is around 0.55, so this is 1 by 1 plus e raised to 0.55 electron volt divided by 0.026 electron volt. So if I do this, then that's 0.55 divided by 0.026. So that's around 21. So roughly this is around 1 by 1 plus e raised to 21. And e raised to 21 is a very huge number. Very huge. And therefore you can easily write it as e raised to minus 21. Okay. Why? Because 1 is negligible compared to e raised to 21. 0.55 divided by 0.026 is around 21. So e raised to 21 is one of the term in the denominator, and other term you are adding is 1 to it. So you can neglect the 1 comparing the value of 1 with the e raised to 21, and you can write it as e raised. So therefore I can directly write at energy equal to the conduction band, I can write the expression approximately as e raised to minus EC minus EF by kBt. So this is a valid approximation. Okay, a very valid approximation. Very valid approximation, and that simplifies our integral. Okay, so now let's go back to the integral, and we are going to put this approximation here. So this is equal to 4 pi, these are all constant, me star all raised to 3 by 2 h cube, then integral ec to infinity e minus ec all raised to half into this one I am going to write it as e raised to minus e minus ef by kBt dE. Okay, so this is an approximate, okay, approximation. It's a valid approximation. That is what I showed you here, that we make a very negligible error in doing this approximation. We get almost the same value. Okay. So now we have this integral to be performed. Okay. So let me just copy this. So we'll put it here. So we are finding out the number of electrons in the, so this is basically the number of electrons in the conduction band, N0. Calculating the number of electrons in the conduction band for N0. So that is this. So apart from the constant, if you look at the integral, now we are going to do some substitution now. The substitution is let E minus EC by kBt, we'll call it as eta, and this is a standard way of solving this integral. Okay, so we call E minus EC. EC is nowhere here inside the exponential, but we need to bring that in terms of that. So how can we bring E minus EC here? So we can just introduce, add and subtract E minus EC. So this is equal to 4 pi into 2 me star 3 by 2 pi h cube integral EC to infinity. Okay, so the limit will also change because we are changing the variable. So what is dE? dE is basically d eta into kBt. Okay, and then limit when E is equal to EC, that is the lower limit, then eta is going to be equal to 0, because E minus EC is basically eta E minus EC by kBt. So E minus EC, that is EC minus EC, is going to be 0, and that's the lower limit. And then E equal to infinity, then eta is also going to be infinity. So it will be eta going from 0 to infinity. Then we have E minus EC. E minus EC is eta into kBt. Eta into kBt. So eta raised to half into kBt raised to half. kBt is a constant, so I will take kBt outside. kBt raised to half, I will take it outside. Or for the moment, let me put it inside, and then finally I will take it outside. kBt all raised to half. Okay, so this is E minus EC raised to half, and then here I need to do some manipulation. That is, first of all, I have to add and subtract EC. So E minus EC, then plus EC minus EF by kBt. Okay, so this way I will write, and when I write like this, then E minus EC by kBt, I can now call it as eta. Okay, so let me write it on the side. So what I am doing is that term I am writing it as E minus EC plus EC. So I am adding and subtracting EC minus EF, that was earlier term, by kBt. So this is equal to E raised to E minus EC by kBt into E raised to minus EC minus EF by kBt. So you can write like this. And the first term is basically E raised to minus eta. So E raised to minus eta into E raised to minus EC minus EF by kBt. Okay. So let's now substitute this here. Okay. So let me just substitute that. So that is E raised to minus eta into E raised to minus EC minus EF by kBt into, now it comes dE. So dE is here, that is d eta into kBt. So there is kBt raised to half here and kBt here. So together, if I combine, it will be kBt raised to 3 by 2. So I can now put that kBt also here along with 2m star. So that will be equal to 4 pi into 2m star kBt, the whole raised to 3 by 2 by h cube integral eta equal to 0. Okay, I can take this term also outside. Okay, so let's take so h cube into e raised, because it doesn't contain eta there, EC and EF by kBt into integral eta equal to 0 to infinity eta raised to half into e raised to minus eta d eta. So this is the integral now we have to solve. So this is much simplified now. eta is varying from 0 to infinity, and this is a very standard integral. Probably you might have learned this integral in mathematics. So I will write what you might have learned in mathematics as gamma function. Gamma function of say n is defined as integral say x equal to 0 to infinity x raised to n minus 1 into e raised to minus x dx. So I hope you have learned this in your maths class, this function. Let me know you have learned this or not. Gamma functions, beta functions, I think it is part of your syllabus. Okay, so in this case, if you compare our particular integral here, it is gamma 3 by 2, and so gamma 3 by 2 you can write, so therefore gamma 3 by 2 is integral x equal to 0 to infinity x raised to 3 by 2 minus 1. Okay, 3 by 2 minus 1 is basically x half into e raised to minus x dx. Now this you can write it as half into gamma half. Okay, and gamma half is given as square root of pi. Okay, so it is basically root pi by 2. Okay. Root pi by 2. So the given integral that we have, I can substitute this entire thing here. This integral I can substitute as root pi by 2. Okay, so that comes like this. So this is gamma 3 by 2. Gamma 3 by 2 is half into gamma half, or you can say that gamma n plus 1 is equal to n into gamma n. Okay. So this is another standard result or property of gamma function. And then gamma half, actually it is evaluated by using some other property, and then you obtain it as pi. So under this approximation, we are so able to get gamma 3 by 2 as half into gamma half. Okay, I have already written this here, so I need to write this. Okay, so therefore, what are we finding out? We are finding out our n0. So n0, therefore n0 is equal to so 4 pi 4 pi was there, 4 pi, and then divided by 2, so that will make it 2 pi, and then divided by square root of pi, so that will make it sorry, not divide by 10, it is multiplying by pi, so it will, you can put the pi also inside the other part, so it is 2 into, so I am putting pi also now inside it, so earlier it is 2m star, so it will be 2 pi m star, 2 pi m star, then kbt whole raised to 3 by 2, then by h cube into exponential of what? E raised to minus of EC minus EF. Minus of EC minus EF by kBT. So this is the final expression that I get. The number of electrons in the conduction band depends upon how far is the Fermi level from the bottom of the conduction band. Okay, so that will decide the value of this expression, the exponential, and then that is multiplied by a constant. So all this thing is a constant. So this I can shorten it as by evaluating the value of all the constant. I can say this is NC into e raised to EC minus EF by kBT. Okay, so I can shorten it like this. Okay, where NC is the value that you get by substituting all the constants, effective mass, kBT, h cube, all this. So for different materials you will have different value. For example, it's also called as the effective density of states. Here NC is called as the effective density of states. Density of state is D of E, but NC here is effective density of states. Now what is the difference? Actually the occupation in the conduction band is actually a distribution, okay, which is given by that red curve which I drawn earlier. So this is how you see the electrons are distributed in the conduction band. So according to this red curve, but by imposing the final expression, what we are saying is that instead of looking at energy states being occupied in the conduction band in a distributed manner, assume as if you have some density of states at this location. Okay, you have some density of state at this location, which is NC, and out of that number of states, some of them are getting occupied. Okay, say this much is getting occupied. So this much is the effective density of states here at a particular energy E equal to EC, out of which a fraction of them is getting occupied, and that fraction is determined by E raised to minus of EC minus EF by kBT. That is what we are saying. So this much fraction, so when you multiply this with NC, so this will give you the probability, and NC is basically the something like the density of states, but it is a constant which is an effective density of states. So we are taking a more simplified picture, saying that all the electrons in the conduction band are staying at the bottom of the conduction band, that is at E equal to EC. So at E equal to EC, all the electrons are staying, and the number of them there is basically given by NC into E raised to minus EC minus EF by kT. So therefore NC is called as the effective density of states. Okay, so this is actually comparing with our earlier expression where we had N of E is equal to density of states of the conduction band multiply f of E, which was basically 1 by 1 plus e raised to minus E minus EF by kBt. Now this I said we could write like density of states into e raised to sorry, here it is plus, so this will become minus E minus EF by kBt. So if I compare this expression with this expression, so by comparing these two expressions you can say that NC is like effective density of states, where E is replaced with EC. Okay, so here it is E, which is varying, which is a variable, where EC is actually a fixed energy. So it is by the comparison of these two expressions we say that we call NC as the whatever is in place of density of states, we have NC. So it is as if all the electrons are sitting at E equal to EC, and there are a lot of states available at that point, which is given by NC, which is called the effective density of states, and out of them the probability, that is f of E or f of EC, so this is f of EC. So out of them this f of EC determines how many of NC is occupied. Okay, so this is the way we are interpreting the result. Okay, so we got this result for N0, and we are interpreting the result as if N0 is equal to, that is total number of electrons in the conduction band is equal to the probability of occupation at EC, E equal to EC, multiplied with some number, and that number is interpreted as the effective density of states by the comparison of these two expressions. Now same thing we can do for finding the vacancies of electrons in the finding the vacancies in the conduction or valence band, so which we call as holes. Okay, so we would like to know the total number of holes. Okay, holes in the valence band. So how do we find the holes in the valence band? That is P0. So P0 is basically also found out with an integral, and now the integral is density of electrons in the density of states of electrons in the the valence band, which is dV of E into the probability of not getting occupied. Okay, so probability of occupying is f of E, but if I do 1 minus f of E, what I am looking at is the vacancies. So vacancies are basically holes. So I am subtracting 1 f of E from 1. So 1 is the maximum probability. From that, if I subtract f of E, the probability of occupation, I will get the probability of non-occupation. So we have density of states, and we are looking at how many of them are unoccupied. Okay, so that is what together we call it as P of E. And if you integrate P of E in the entire valence band, so how do we perform the integration? We need to start from the bottom of the we need to start from E should vary from, say, from the bottom of valence band to EV. Okay. And we don't know exactly where is the bottom of the valence band, but if you look at 1 minus f of E function, that function also becomes 0 when energy is much lesser than EC. Okay, so let's look at that. So earlier we plotted f of E. So let me plot that again. So f of E is something like this. Like this. So this is f of E. It is equal to 1 here, 0 here, and there is some point where it is half, and that is what we call as EF, or Fermi energy level. Okay, so this is E. Okay, so now at t equal to 0 degree Kelvin, I said it is something like a step function like this, and at some finite temperature it will be a smooth function like this, which goes to zero at higher energy like this. Exponentially it goes to 0, and here it goes to 1. So now if I do 1 minus f of E, so let me take 1 minus f of E, and let me plot it on the top of this. So if I take 1 minus it, f of E, what will happen? So wherever it is 1, it is going to be 0. So all these places it will be 0. Wherever it is 0, it will be 1. And then where it is half, it will also be half. So it will be like this. Okay, so this is how the expression. So this is our 1 minus f of E function. So it's just subtracting 1 minus f of E. So f of E is given as this purple curve. So if you subtract that from 1, you will get this 1 minus f of E. And as you can see that this goes to 0 downward. So our EV is somewhere here, and our EC is somewhere here. Okay, so we are integrating from EC to bottom. Okay, and you see that when you multiply dV of E, if I draw, dV of E is something like this. This is dV of E, just like we had so this was our dC of E, conduction band density of states, and this is dV of E. So by multiplying dV of E with 1 minus f of E, what we are going to get is, if I show only that portion, that is dV of E into 1 minus f of E. Okay, so this will be, so that is I am multiplying dV of E, which is this orange curve, and then I am multiplying 1 minus f of E, which is the red. So product of red and orange. So that I am drawing. So I will get a function which initially rise downward, and then because the exponential goes to 0. So this is my P of E. So this is my P of E. Okay, so which I have written here. So P of E is basically this, and then if I integrate for all the energies up to EV downward, then I will get P0. That is the total number of holes. So So total number of holes is determined by two things. One is the states, how many states are available, multiplying what is the probability of making it vacant. Okay, vacancy is 1 minus f of e. Okay. F of e is occupancy and 1 minus f of e is vacancy. So this is the probability of being vacant. So that multiplied by the number of states which are totally available. Out of that, some are occupied, some are not occupied. Our interest is in how many of them are not occupied. So that is P of E. Integrate them, we will get total vacancies inside the valence band. Okay, so now let's continue this. So let's substitute. So as before, I can say it can be integrated from minus infinity to EV and then 4 pi into 2m. For holes I am putting H here, M star, or sometimes you can put P also, N for electron and P for holes, or H for holes I am putting here. Divide it by H cube, then I have EV minus E the whole raised to half into, now this 1 minus f of E, so let me also talk a little bit about 1 minus f of E. So we know f of E is basically 1 by 1 plus e raised to e minus ef by kBt. So that is f of E. So 1 minus f of E is 1 minus 1 by 1 plus e raised to e minus ef kBt. So that is equal to 1 plus e raised to e minus ef by kBt minus 1 divided by 1 plus e raised to e minus ef by kBt. So this one cancel. So what we have is basically this is equal to e raised to e minus ef by kBt. Divided by 1 plus e raised to e minus ef by kBt. Now in this case our energy that we are integrating are all below EV. Okay, is below EV. So EV is around half of EG below EF. So this is EG by 2. So EV is around half of EG by 2, and EG by 2 is much greater than, around 21 times greater than kBt. Okay, so therefore our in the region of our interest where E is much below EF, E is much below EF means E minus EF is going to be of the order of minus EG by 2. So this is of the order of, so E raised to, you can write it as minus EF is above minus E by kBt divided by 1 plus E raised to of the order of minus EG or that much with a minus sign. Okay, so it is of the order of this. Now this is a very small number. Why? Because it is like E raised to minus 21. Earlier it was plus 21, now it is minus 21, okay, which is negligible, it is 0, okay. So therefore you could write this to a very good approximation as e raised to minus EF minus E by kBt. This is our approximation, which is a very valid approximation, because E minus EF is of the order of Eg or more, okay, or minus Eg or more, magnitude, or we can say minus of a quantity which is Eg or more, which is much greater than kBt, around 21 times at least greater. So e raised to minus of 21 is almost equal to 0. So you neglect, and now you are neglecting the second term with respect to 1. Earlier we neglected 1 with respect to the other term, because that was a huge term. So now we are neglecting the negligible term corresponding to 1 with respect to 1, and then we write it like this. So this is what we are going to use in the integration to simplify. So EF minus E by kT. So e raised to minus EF minus E by kBt. So this is our 1 minus 4 approximation. Alright, so now we have something very similar to what we did earlier. Again we have to use a substitution, and the substitution is also like very similar to what we did earlier. Let's say let say eta. Now in this case eta we will define as EV minus E, okay, whatever is here, divided by kBt. Now this means dE is going to be minus d eta into kBt. So there will be a negative sign, and then we have to look at the limits also. When E is equal to minus infinity, then eta is equal to what it will be. E is minus infinity means eta is going to be plus infinity. Okay. Then if E is equal to EV, that is the upper limit, E is equal to EV, E is equal to EV means eta equal to 0. Okay, so now let's substitute all of this. So therefore P naught is equal to, so now minus infinity becomes plus infinity, and EV becomes 0. Okay, let me just take all the constants outside. So 4 pi into 2 mh star, that is the effective mass of hole, divided by h cube, then my plus infinity to 0, eta varying from plus infinity to 0. Now EV minus E all raised to half, so that is eta raised to half into kBt, kBt raised to half, yeah, kBt raised to half into this expression. What I will do is I will write it as, okay, so let me also show what happens to that expression. So that expression is basically e raised to minus EF. I need to bring EV into the scene. So what I will do is I will minus EV and then plus EV divided by kBt. Okay, so this expression I am taking and rewriting like this. So which is basically e raised to minus EF by minus EF minus EV by kBT into, now if I look at the remaining thing, it is e raised to minus of eta. So that is what I am going to substitute. So that is minus EF minus EV by kBT into e raised to minus eta, and dE is minus d eta into kBT. This minus sign I can use to interchange the order of limits. Okay, I can make the upper limit as lower limit by absorbing this minus sign, and the constants I will take it outside. Like before, kBT is raised to 3 by 2, I will put inside. So 4 pi by h cube into 2m star kBT raised to 3 by 2 into, I can take this thing outside because it is independent of eta. So it is e raised to minus of EF minus EV by kBT into integral from eta going from 0 to infinity. I absorb the minus sign, and then I am saying eta raised to half into e raised to minus eta d eta. Again, this is basically gamma 3 by 2, which could be written as integral x is equal to 0 to infinity x raised to 3 by 2 minus 1 into e raised to minus x dx, which can also be written as half into gamma half, which is root by 2. So I will substitute that root pi. Already there is a pi there, so I can absorb the pi also inside the bracket containing power of 3 by 2. So, and then this will become 2 into 2 pi m star kBT raised to 3 by 2 divided by h cube into minus EF minus EV by kBT. Now this thing I will write it as like before. This I will define as NV, density of states in the valence band, and that is NV into e raised to minus EF minus EV kBT. So comparing this with the other expression, which is dV of E into e raised to minus E minus sorry, yeah, what was it? EF minus E by kBT. So this was basically 1 minus f of E approximation. It was e raised to minus EF by A. Yeah, this one. Okay, so e raised to minus EF minus E by kBT. So this was our density of states, and this was probability of not occupying the state. So therefore our NV is basically 2 into 2 pi m star kBT raised to 3 by 2 by h cube is called effective density of states in the valence band. Okay, so this is effective density of states in the valence band, and we earlier had effective density of states in the conduction band, which was 2 into 2 pi m star. So here it is m star of whole, and here it is m star of electron, kBt. Otherwise both are same. So they are determined by effective density of states in the conduction. So what we are saying is that so this picture is like we have lot of density of states at the top of the valence band, which is Nv, and the probability that that is not occupied is given by 1 minus f of E, where E is equal to Ev. So here this is basically 1 minus f of Ev, minus f of Ev. Okay, so therefore Nv is called as the effective density of states in the conduction band. The only difference between Nv and Nc is the conduction band and valence band effective mass is going to be different, which is basically the curvature of the band structure. Okay, at the bottom of the conduction band is mh star, and the curvature of the top of the valence band, that is negative, but we take the absolute value of that, which is mh star. Okay, or we will call it as effective mass of hole. We have found N0 and P0 basically. So this is P0 what we found. So this is an important expression. Number of holes in the valence band, and the reason why the holes are going to be in the valence band is because the electrons went from the valence band to the conduction band, making some of the states empty or some of the states vacant, and P0 is basically the count of the number of vacancy in the valence band. And so current can flow because of holes through the valence band, and current can flow because of electrons in the conduction band, which we saw in the last class, in the last day, when we discussed the electric, in the presence of electric field, there will be a creation of asymmetry in the occupied state in the conduction band as well as vacant states in the valence band. So that can give rise to current. So there can be current through the valence band and current through the conduction band, and ultimately that current is going to depend on N0 and P0, the number of electrons. Okay, of course it will depend on the asymmetry, but it also depends upon the number of electrons and number of holes. So at higher temperature, what would happen is that more and more electron hole pair will be generated. That means more and more electrons from the valence band will find energy to go to the conduction band, and thereby creating more number of vacancies in the valence band and more number of electrons in the conduction band. Okay, so the conductivity of the material, semiconductor material, increases as a strong function of temperature. Okay, so if you heat a semiconductor, so that I can say as a conclusion, therefore if we heat a semiconducting or semiconductor, then what is going to happen is we are going to effectively increase the value of N0 and P0, because N0, you see Nv, you see that it is proportional to T raised to 3 by 2. So as temperature increases, Nv and Nc will increase. The value of Nv, Nc, which is proportional to T raised to 3 by 2 increases. If you heat the semiconductor, the value of Nv or Nc, which is proportional to T raised to 3 by 2 increases. And the other thing that is going to happen is the exponential, and f of Ec, which is equal to e raised to minus E minus Ec by kBt, and 1 minus f of Ev, which is equal to e raised to minus EF, so this is also EF, EF minus EF minus EV. Okay, I think here it is EC minus EF, EC minus EF. Yeah, so this is EC minus EF for conduction band, F of EC, and 1 minus F of EV is EF minus EV kBT. Okay, increases and F of EC and 1 minus F of E. So this is basically the probability of vacancy and probability of so this is probability of occupancy in conduction band, or the bottom of the conduction band. Then this is probability of vacancy in valence band. So this also increases. Why it increases? When T increases, the denominator of the exponent increases and there is a negative sign. So this become e raised to a negative of a smaller quantity. If it is a bigger quantity, negative of bigger quantity, this is effectively much smaller. But when T increases, what will become e raised to, it will tend to e raised to 0. E raised to 0 means 1. Okay, e raised to minus 0 or minus a smaller quantity. So that way the entire functioning. So the product of these two is what is N0 and P0. So therefore, from this expression, what we can say is that is N0 and P0 strongly depends on, they are strong functions of temperature, and they increases with the increase of temperature, because both way it increases. One is NC and NV increases, the other is probability also increases. It increases with the increase of temperature. Okay, and thereby making the semiconductor more conductive. Okay, conductivity of semiconductor increases with the temperature, and the reason is that N0 and P0 increases with temperature. So we will continue from here.